All right. My name is Miguel Torres. I am part of Osbe's class over in summer of 2025 here at UCF. Um, that's a pretty formal intro, but right now we're gonna do project two of fluid mechanics here. So let's get started. First thing I'm gonna do is set this thing to 2D here, and then open it up in Discovery. So there you go. Um, Now, while I'm waiting for this to open, 'cause it does take a little bit to open, um, the purpose of this simulation for Project 2, if there are any outsiders aside from Osby looking at this, um, the purpose of this is to find boundary layer or make a simulation over a flat plate. So we're trying to analyze the boundary layer that forms as air go over a surface, and in this simulation that surface will be a flat plate. So yeah, and since we're doing a flat plate, our domain, the negative in which we're gonna, you know, our we're interested in simulating, it will just be a rectangle. So here you go. And then now next thing we do is dimension it. This is pretty straightforward. And our assignment here has to be a length of 1 meter. The height is not really stated, so you can use pretty much any height. I'll just go 20 centimeters here. That looks good. You can press D or click here to get away from the sketch, and it will automatically create a surface. In this surface, what you're going to do next is click on the edges and name them, and label them. So here, this will be named inlet, outlet, wall, and then this top one, I'll name it Atmo, short for atmosphere. This is just open air. So there you go. Once we have our name selections, we can close this. Next thing I gotta do is open up the mesh. And there you go. Opening the mesh, it might take a bit to just open up the file and also mesh. So yeah, do bear with me on this. So. All right. Now we're gonna start meshing. So before we mesh, we gotta set our refinements. I'm gonna do a sizing refinement on inlet and outlet. That's okay. Number divisions, and then for the inlet and outlet, I played with this a little bit. For me, what I find works best is a number divisions of 400. And since we're interested in the boundary layer, we have to focus our smaller cell sizes to the walls, to the wall here. Because we don't want it super fine, like away from the boundary layer, because we're just capturing open air. You want to capture that boundary layer. So that's why I'm going to do this. So we're going to set a bias factor of, oh, let's do 10 and then 10 here so I could see what's going on. You can see here that with the bias factor, we could set our bias, because you could set it here any direction you want, any way you want. We're going to set the bias where the smaller cells are is toward the wall. And as you can see here, it does the opposite. If that happens, just click on reverse bias, click on the edge you're interested in, and click apply. That's it. And there you go. And now we could put in our real values. So I'll set a bias factor to 100, number divisions of 400. Here's what I find works best for me. And oh, of course, you got to name it inlet outlet. This is in case if anything happens, you just go back and see that everything's organized. So now I'm going to create a new sizing. This will be for the wall. Name here. There won't be a bias here. Rather, instead, we're just going to do number divisions. This will be 4,000. Yeah, and then, well, let me double check on that. No, it was 2,000. Yeah, I have it here in the notebook. So, yep, that's good. Let's start a new one. This one will be for the atmosphere, Atmo. And I'm going to click on that wall here. Now, it is important that we do this. Set the refinement to the atmosphere, even though we're not really interested in it. Because if we don't, which, well, I'm not going to show you because it might take a little bit to mesh. I don't want to waste more time. What it will do is just make a weird sort of mesh where it would make it super coarse in here, and then later you see it super fine in here in this edge, and you just get this weird pattern going on. So that's why I'm setting a refinement here. And we're going to do number of divisions again, and we're going to do 500. So, yep. And then finally, of course, we got to do is face meshing. There you go. Now, there is a way of doing boundary layers here in ANSYS and doing it 2D, especially on an airfoil, where you go to insert and you click on inflation. But the problem with this is that if you use inflation, you could only use triangular meshes. So that means we can't use the face meshing refinement here, where we'll just keep everything quadrilaterals or rectangles, which is what I want here. So instead, I have the boundary layer focus using the inlet and outlet and the bias factor here. Now we mesh, and yeah, this we're gonna have to give it some time, or not. That was surprisingly very quick, very nice. But yeah, you can see what the bias factor does. The top here are more coarser, and then as you get smaller, well, closer to the wall, they get very, very small. This is what we want, because we want most of our focus down here. So, and also pardon this mouse glitch I have. This is caused by the GPU, so just don't mind it. Now we can close it. I'll wait till it's fully closed. Alright. Again, setup, open it up, self decision, and then 6 processes, and click start. All right. Now we're here in Fluent. Leave these as normal. We're doing a pressure-based simulation, and it will be steady state. So just don't touch that. Here in models, viscous, since we know our flow is laminar, we're just going to choose laminar here. Click OK. That assumption can only be made if you know that it truly is laminar, which we know it is because, well, in our next segment here, our inlet velocity will only be 2 meters a second here. And with that velocity and also the parameters that we're going to use for the air, which for us will be a density of 1.2 and a viscosity of 1.8 e to the negative 5. There you go. So with these parameters, your Reynolds number will be way less than, you know, the critical Reynolds number needed for turbulent flow. So we could make the assumption that the flow here is laminar. And also because the assignment stated that you have to use laminar, but yeah. All right. Now, everything's here is good except for the atmosphere. I don't want the atmosphere getting a boundary layer, forming a boundary layer. So what we're going to do here is change the atmosphere from wall to symmetry. Now you could use pressure outlet for this. However, I tried a pressure outlet the first time I ran this, and my residuals started looking like a transient simulation where you get that sawtooth pattern. It isn't really great for a steady state simulation. You want it to really drop down smoothly. So I find that symmetry works best for me. There you go. Next thing I'm gonna do is change the convergence criteria for the simulation. I'm gonna go 1e to the negative 6. This is just a pretty decent number. Click OK. The next thing I'm gonna do here is create a coefficient of drag. Drag coefficient, wall, and make sure your force vector is in the correct direction. In this case, it's along the x direction, so that's good. And then change the name, and I'm gonna put print console. There you go, click OK. And yeah, that is good. Now we could initialize and then run it. There you go. Yeah, don't mind that. Sometimes my ANSYS just does that for some reason. All right, number of iterations. Set this as like 1,000, whatever. But if you set your mesh correctly and you put your input conditions correctly, then it should converge. Like for me, it will converge around 80 iterations. So it'll be fairly quick. have to stop it. I have forgot something, and it's something I've always forgotten, and that is my reference values. This will be important because if I don't change this, then my coefficient of drag would be off. It wouldn't be correct, and I learned it the hard way before. So yeah, just give it a minute. Okay. Yeah, I've just remembered something. Gotta go to reference values here, physics, reference values, and put compute from inlet. This is important because if not, then it will try computing from some random point, and then your coefficient of drag would be way off. Reference zone, I'll just leave it like that. And there you go. Now we can recalculate it and continue. Yep, and there we go. Yep. All right, our simulation is now done. Before we could close this and move on to the post-processing application of ANSYS, we got to get our results for wall shear stress and skin friction. Now, coefficient drag, and skin friction coefficient. There is a way of getting that data in the CFD post application. However, me personally, I'm not that skilled with the CFD post application in ANSYS. Whenever I run simulations, I normally tend to use the results tab over here in Fluent. But we will still use the application, the CFD post application, to get our velocity profiles. So yeah. So here in plots, new XY plot. This one I'm gonna go wall shear stress. Go to wall fluxes, wall shear stress, and then click on wall, save and plot. There you go. You can see the wall shear stress along the wall. Next thing I'm going to do is skin friction coefficient. So that's CF, wall fluxes, and then skin friction coefficient. click on wall, plot. There we go. Pretty easy. And yeah, that's pretty much it. Next thing we could obviously do is just run the report for the coefficient of drag. If I click compute, you can see it here is 0.0043. That's a reasonable number for a flat plate, so pretty happy with that. Close the application. All right. Now open up the results tab. Okay. All right. Now do bear with the black background. I changed it here because my eyes do hurt. So yeah. Okay. So now in here we're gonna do our velocity contour, velocity profile, velocity vectors, and yeah, that's it. Just those three things. So first I'm gonna do is vectors, velocity vectors, location 71. Leave all that as is. I'll change the color here. And then symbol 0.01. If you're using my settings for the mesh, I recommend using 0.01 in symbol size. And this is a symbol style. I personally like Arrow 2D. So there we go. And yeah, now if we zoom in, you could see these vectors. It's very small because the mesh I have is very fine, so that's why it's very small. There you go. But yeah, you can see the boundary layer forming with the velocity vectors, which is what we want. It's what we expect here. I'm gonna edit this guy here. None, none, horizontal. 25. There you go. Yeah, there you go. Alright, next thing we gotta do is velocity contour. Search one. This time I'll do, let's do 20 contours here. I just go BGR modern. I like this color quite a bit, so yeah, it's good. Click apply, and bam, there you go. Oh, that's pressure. Velocity along the x-axis, what we're interested in. There we go. That's more like it. Yeah, you could definitely see the boundary layer forming. So that's good. And now finally, we get the velocity profiles at certain locations. All right, line 1. In our assignment, we're interested in x locations of 35 centimeters and 75 centimeters. So this one's a 35 centimeter location. So number of samples, this should be a pretty decently high number. I'm gonna go with 400 here. Okay. And then we set a new line, 0.75, 0.75, 0.2, and again 400. There you go. Looks good. Now we make a new plot. Velocity profile. On data series, we do 0.35. Line 1. X equals 0.75. Line 2. X-axis will be velocity along the x direction, or velocity u. Y-axis would just be y, the y position. And there we go. That right there is our velocity profile here in the boundary layer. This looks pretty reasonable. You can see it increasing and increasing as we go up until we reach the boundary layer thickness, and then later it just goes down like that. So that's as expected. Yeah, that is pretty much it for project 2, and that is how we ran our simulation for this assignment. Thank you very much.